so it is 5:30, so I'm going to go ahead and get started, jump right into it. Hopefully everybody, well, actually your class, you're good. It was the other class that actually has tonight to finish their face-to-face test. But anyways, we are going into chapter 8, and chapter 8, if I can stop yawning. Ugh, not there. Chapter 8 is called Conservation of Energy. And as always, of course, you want to start off by reading the chapter opening question, taking a poke at what the answer is, and then using that as a focal point as you read throughout the rest of the chapter. I'll tell you the subsections are conservative and non conservative forces. 8.2 is potential energy. 8.3 is mechanical energy and its conservation. 8.4 is problem solving using conservation of mechanical energy. 8.5 is the law. Excuse me. Is the law of conservation of energy. 8.6 is energy conservation with dissipative forces solving problems. 8.7 is gravitational potential energy and escape velocity. 8.8 is power. 8.9 is potential energy diagram, stable and unstable equilibrium. And 8.10 is gravitational assist, gravitational slingshot. All these sections should be read and tried your best to understand, but be advised I'm leaving the 8-9 section, potential energy diagram, stable and unstable. That's a pretty straightforward reading, and I think it makes perfectly good sense. So I'm not going to be talking much about that in general. The gravitational assist and gravitational slingshot, I'm not going to test you on that, but it may, excuse me, it may come up in practice tests and homeworks. So, and not only that, I'm doing in my chapter 8 a little differently than your textbook author. I'm starting off with what we call the gradient theorem or the line integral, path integral theorem. So let me start by sharing my screen with you for today. And here it is. Okay, so it should pop up any minute now. There we go. Okay, so I've taken the time to write out a rough version of what I consider to be the gradient theorem or the fundamental theorem of line integrals. It's a fundamental idea within the vector calculus realm, which I told you was more or less invented by two or three different people at one time around the 1830s up through 1860, maybe. One of them was, I think his name is Joseph Gibbs from Gibbs Free Energy fame from America. I know he is American, and I know he's one of those people whose last name corresponds to one of the energy functions, and I'm pretty sure it was Gibbs. But just in case, I just wanted to hedge that in case I misremembered. The other one was a guy by the name of Oliver Heaviside, and he actually had no more than more or less a high school education. But he was a natural born math aristocrat, if you will. So, anyways, the fundamental theorem of line integrals is basically this theorem, if you will, that if one part is true, then all parts are true. And because of its ramifications, we have a very specific prescription about how we could go about taking a force field if it meets certain criteria, specifically the criteria that we use to define a conservative field. And it doesn't have to be force, by the way, even though that is one of the options. Another option is the one that we use in the 242 class, which is the electric field. And that can be conservative as well, even though it's not a force field. It's actually in units of force per coulomb. And for that reason, it's a little bit different, but still we could use that similarly. Ugh, I am sorry. I don't know why these yawns are coming on. But anyways, let me go ahead and read it, and I'll try to make some sense of it as we go along. If any one of these statements are true, all of them are true. One, a vector field F is conservative. So what that means is let's imagine a vector field that we're going to call F. And when we say something is a vector field or a field in general, what we mean is to every point in space, every x comma y comma z in parentheses. That's the way we specify a point. But for every point in some fraction of space, if we define a quantity at each one of those points, then that is called a field. If that quantity happens to be a vector quantity, Then it's a vector field. If that quantity happens to be a tensor field, a tensor quantity, then that field would be a tensor field. If it happens to be a scalar, then it's a scalar field. So, like if I imagine my room here, and maybe I establish a origin, an x-axis, a y-axis, and z-axis, and then I go to each point in the room and say, okay, here's x1, y1, z1, and I measure the temperature right there, and then I submit that as the value for the temperature field. And then I do that for all the other points. And hopefully I see some pattern where I can make a mathematical expression. But the main thing is when you're talking about a field is something that takes in a data point or more specifically a point in space and spits out a value. The value is the field value. That field value might be a vector field. That field value might be a scalar field. So, for instance, a temperature field would obviously be a scalar field. A force field could be a scalar field if you just map the magnitude of the force into the particular points in space. But if you map the magnitude and direction, then it would become a vector field. Another one, like I said, is the electric field. So a vector field F is conservative. That's one of the statements. If that's true, then they're all true. And then the rest of these are ways you can determine whether or not it is a conservative field. Number two says the curl of f is identically zero. Now, the curl is a mathematical operation, and this is actually it. I've talked to you about this gradient operator before, this upside down triangle. That's what we call a vector operator. And to be honest with you, what it is, at least in Cartesian coordinates, is it's a upside down triangle that is supposed to leave a blank space to its right, because what happens is the vector operator can operate on something. It can operate on a scalar, in which case it's called the gradient. So a scalar function like f of x or f of x, y, z or something like that, if you put the gradient operator next to that, that will spit out a vector, and that vector is called the gradient of the field f. You can also put a dot next to it for a dot product, and then you'd of course have to have a vector on the other side. So then you would have the gradient dotted with some field like f, and in which case that's called the divergence of f, and it really is a measure of how much the field either uh, comes together at a single point or actually emanates from a single point, one being positive and the other being negative. And then a third thing you can do with it, and this isn't all, by the way, a third thing you can put to the right of it is a cross product. And that's from the cross product of that we learned in 241, like in the chapter on torque. In that case, you'd have like del cross F, like you see here, and that is called the curl of the field F. And when I say identically zero, you could, for instance, calculate this del cross F using a matrix. The matrix, by the way, would have, you'd have to take the determinant of a matrix. The first row of the matrix would be I hat, j hat, k hat. The second row of the matrix would be the partial derivative with respect to x. Notice I just said the partial derivative. I didn't say it was acting on anything. So the first component is literally the first uh, column in the second row is a partial derivative with respect to x. The second component in that second row is the partial with respect to y, and that third component is the partial with respect to z. And then in the third row of that matrix, whose determinant you're going to take would be f sub x, f sub y, and f sub z. That would be the three entries. And then you calculate that determinant, and you get what's called the curl of the f. Now, of the field. Now, if you got that that was identically zero, it would just come out to be zero, period, and you wouldn't have to do anything. If, on the other hand, you saw that it had certain values of x or certain values of y or certain values of z, that if you substituted in a specific x or a specific y or a specific z, or maybe specific x and y or specific y and z or specific x, y, and z, if you had to do that to make it equal zero, then it's not identically zero. Okay, that's what we mean by that. So evidently, one of the tests for a field being conservative is testing the gradient. The gradient of the field should equal zero identically. Another one is, and this one is a little bit different because it doesn't actually give you a test. It says, hey, if it passes this test, then you can do this. And here's what it says. It says, if a vector field is conservative, then there exists a scalar potential u such that f is equal to the negative gradient of u. So that tells you that, hey, there is a stand-in function that's a scalar, and you can use that to represent something about that force field or that vector field that you had, only you can do it with scalars, which will save you a lot of trouble. And that's what we're learning about in this class. We're going to learn about potential energy and some other things. But what you see is the way you get the force back out of it once you have the scalar potential is you take the gradient of the scalar potential u and you multiply it by -1. And as I told you, when you let this gradient operator act on a scalar function, it spits out a vector. And in fact, in this case, the vector would be negative partial of u with respect to x I hat plus negative partial of u with respect to y j hat plus negative partial of u with respect to z k hat. That's what the gradient of f would be. Number 4 says the work done by F, work equals the integral from A to B of F dot dl, is simply the negative of the change in potential energy, negative delta U. So W is equal to the integral from A to B of F dot dl, and of course F is the negative gradient of U, so you're going to get negative integral from A to B of the gradient of U dotted with dl, and you might notice that this looks like an integral of a derivative, and it is, and for that reason this is sort of like the fundamental theorem of calculus that shows the integral of a derivative is equal to the original function, and that's what we're saying here is the integral of this gradient derivative is equal to the function u evaluated at b minus the function u evaluated at a, and then times -1. So you'd have to put it in the opposite order to keep it positive, and that's what they did here. And that's equal to the negative gradient of u. Now, that one is, again, not so good as a test to see whether or not the field is conservative, but rather it tells you a way you can go about calculating what the scalar potential is. Specifically, it's telling you, hey, if you calculate the work done by the force field in going from A to B, that will be equal to the negative of the change in potential energy. Therefore, you can set the negative of the change in potential energy equal to the results, and from that, that can allow you to figure out what the function potential energy is. Number 5 says the work done in moving from A to B is independent of the path taken. Now that's a real test. That's a test that you can do to see. And if you actually integrate from A to B and you find the result is just the subtraction of a scalar function at two different places, then you've shown that that is a conservative force. The work done in any closed path is 0. That is another test you could do to test whether or not the field is conservative. You just calculate the work done in a closed path. That means you can follow any routes you want as long as you start and end on the exact same spot. If that is 0, then you know it's a conservative field. Just like if the work done and going from A to B didn't depend on which path you took. You could go from A to B by going along the x-axis and then the y-axis. You could go along the y-axis and then the x-axis. You could go along a straight line like that between them. You could take a parabola between them. You could take a upside down parabola between them. Anything you wanted, and all of those would always give the same results. And then finally, this part 7, I'm sort of trying to make it work in such a way that you, one, might have some understanding of why it's so, but two, because most of you haven't had differential equations, you won't necessarily know the value of this, but I want to show it to you in case some of you have had it or currently taking differential equations. But basically, the argument is this. If you try to calculate the differential change in the scalar potential u, the method that we use to do that, we learn in Calc 3, and that is the partial of u, because u is a function of x, y, and z, for instance, in Cartesian coordinates. So the partial of u with respect to x multiplied by a differential change in x plus the partial of u with respect to y multiplied by a differential change in y plus the partial of u with respect to z multiplied by a differential change in z is equal to the change in the scalar potential. And of course, a lot of times when we're trying to study this, we want to know specifically the answer when the change in u is equal to zero. So that's why I put the equal zero here. Now, to make this a little bit more understandable, what I wanted you to remember is that the negative gradient of u is supposed to be the force. So the partial of u with respect to x is actually the negative of f of x, and the partial of u with respect to y is the negative of f of y, and the partial of u with respect to z is the negative f of z. Meaning, and I'm not meaning of z, but I mean the z component of f, and the y component of f, and the x component of f. So the reason why I bring that all up is because when you look at what the cross product is, the cross product is us basically taking the partial of f sub x with respect to y and taking the partial of f sub y with respect to x and subtracting them. Now, if you were thinking about that this way, if I'd taken the partial of f sub x with respect to y, then what I'm really doing is taking the second partial of u with respect to x and then with respect to y. And then if I'm taking the partial of f sub y with respect to x, then I'm technically taking the partial of u with respect to y, and then, of course, the second partial of u with respect to x, so that those two should automatically be equal to zero, because it turns out that in most cases where we're dealing with functions that are routinely used in everyday life, we find that it's very randomly, or it's almost never the case where the partial of u with respect to x and then the partial of u with respect to y is different if you take it in a different order. So that automatically tells you that this gradient of f equals zero is exactly what happens to this to make it what we call an exact differential equation. So if you've had differential equations, or if you're currently taking them, you probably are already to the point where you've covered exact differential equations, and you'll know this, that they're normally some function times dx plus some other function times dy, and it's usually just those two. They don't normally do three, but you could do them in differential equations. But your test is, does the derivative of this one with respect to y equal the derivative of this one with respect to x? If it is, then you say, okay, yeah, this is an exact differential equation, and we've got a very straightforward process to go through to solving it. So that's the big thing here. The most important part, or the most part that's the part that's most important for us to move forward in this chapter, is really this part 4 that tells us how to find the scalar potential that can be used to represent f, and then how to actually compute f from that scalar u, as well as how to test that that function f is a conservative field, specifically through the gradient test, or specifically through the path independence test, or specifically through the closed path work done process. Anybody have any questions on that before we move along? Okay, so your book's not completely distinctly different from what I'm doing. He's sort of hinting at the same things I am, except I took the time to actually write out the theorem. And I'm not necessarily saying that my way's smarter or his way's smarter. I just know that it left me with a lot of questions when I went over this section. So I thought it'd be best to sort of explain it a little bit, and just know you don't have to know all this, but it's something that I want you to have in your head. So when you get further along in your physics and engineering studies, or even chemistry studies, that you'll have some reasonable understanding of where this came from. So, by definition, this is what your textbook author says. By definition, we call any force a conservative force if the work done by the force on an object moving from one point to another depends only on its initial and final positions of the object, and is independent of the particular path taken. So that is, in fact, item 5 in my theorem. So you can see that it's not completely separate from what I was talking about. It says, Giancoli then says, we can give the definition of a conservative force in another completely equivalent way. A force is conservative if the net work done by the force on an object moving around any closed path is zero. So if you do any closed path from A to A, for instance, and that work ends up being zero, then it's a conservative force. If you'll notice, that happens to be equivalent to theorem item number 6, and so on and so forth. He gives some examples of conservative forces. The examples that he gives are the gravitational force, the elastic force, which is that Hooke's law that we learned about earlier, F equals negative K times X, and the electric force. And more specifically, what we're going to use is not the electric force, but the electric field, which is measured in newtons per coulomb or volts per meter. Non-conservative forces include friction, air resistance, tension in a cord, motor or rocket propulsion, or a push or pull by a person. Okay? So, with all that being said, I'm going to show you how to go about calculating specifically uh, the potential energy function for the gravitational force m times g, i.e., the weight. So, let me show you. What we're going to do is we're going to imagine a coordinate system like this. Here's X, here's Y, and we're going to imagine we have a mass right here, and its mass is M, and it is located at, let's say, a height Y1. Similarly, the mass sometime later might be up here at position Y2. Now, we could consider this position, for instance, A, and this position up here, B. And what we want to do is use our theorem that we just learned about. And that theorem says the work done by F is simply the negative of the change in potential energy, negative delta U. So we're going to do that. Now, what we're going to do is we're going to imagine that we're going to apply just a big enough force to make it move upward. Okay. And we're going to calculate the actual work done by that force, the weight equals mg. We're going to see what work is done by that force mg, and that will give us a potential energy function. So I should also include a vector for the force that is weight is equal to mg. That's the magnitude. It happens to be pointing down, and we're going to move it from y1 to y2. And we're going to do it in such a way that it goes really, really slowly. So what I'm imagining here is I'm going to apply just a big enough force where the acceleration is free to be zero. You know, Newton's second law says the summation of forces is equal to mass times acceleration. If I put just enough force on it so that the net force is zero, then the acceleration will be zero. The reason why I want to do it that way is if I give it an acceleration, then I'm actually going to be making it move, and it's going to actually, like we learned in the last chapter, it's going to change its kinetic energy. And of course, changing kinetic energy is a result of work being done. We don't want that. We want just enough work to take it from point A to point B. So you can sort of imagine me pushing up, pushing up, pushing up, pushing up just a little bit harder each time until finally I feel like if I give it a little bit more push, it's going to start to accelerate. And then we sort of wait around for a random molecule to fly by and bump it up a little bit. And then we wait again for another random molecule to bump it up again. But each time we're sort of holding our finger on it so it doesn't go back down. And then over a very long amount of time, it'll eventually move from Y1 to Y2. So now I'm going to calculate that work done. Uh, Negative delta U is equal to the work done against friction, or excuse me, against the work done by the conservative force, and that's equal to the integral of F dot dl. Now remember, this is a line integral, so again, we're supposed to choose the direction of integration, and we're supposed to evaluate the integrand on the actual path of integration. Our path in this case is going to be along the line x equals 0, and it's going to go from y1 to y2. The force that we're actually applying is one force, and that's going to be just big enough. It's going to be a force whose magnitude is mg. But in this case, we're actually calculating the work done by the gravitational force, which points in the negative direction. So in that case, I'm going to say it's equal to the negative or the integral of, in this case, the force is negative mg j hat. So that's our force. And I'm going to dot that with a DL, a differential line element. Now, the differential line element has to be parallel to the path I'm taking. I'm taking the path x equals 0. That's a vertical line. And you might recognize that as, since it's x equals 0, it's actually the y-axis. So it seems reasonable that we should let the change in length, the itty bitty change in length, to be dy as opposed to just some random dl. So I will take that to point in the positive direction. That's going to be dy times j hat. And now I'm going to let, since I went ahead and let the DL point in the positive coordinate direction, I'm going to set the limits of integration to point in the actual direction of integration. So I'm actually going to integrate from y equals y1 to y2, which, by the way, if I had chosen to do the DL pointing in the direction of integration, I would have still gotten dy hat, and I still would have had to use the default for the limits of integration, which would still be y1 to y2. So it's really, in this case, when you happen to be going in the same direction as the positive coordinate direction, the line integral has almost no danger. So it's really easy to get the impression that you know how to do line integrals because you consistently get them right even when you're not thinking about it. All right, now, how do we do this? Well, as I told you, the dot product is a linear operation, so that means that we can pull out all the scalar stuff out in front. And the m and the g are scalars, as is the negative symbol. And they're scalars, so they actually are constant, so I can literally pull them out in front of the integral itself, and I get negative mg. And then the dy, that can't go past the integral, so I'm going to put it right here. But then I'm left with the j hat dot j hat. And of course, j hat dot j hat is just 1. And I get the negative mg, negative mg times the integral from y1 to y2 of dy. And of course, the integral of dy is just y, so I get negative mg times y2 minus y1. Now remember, this is negative delta u is equal to w. So from that, and actually I'll use the therefore instead. Therefore, I'm going to say this is negative of u at 2 minus u at 1. In other words, delta always means final minus initial, and I've got a negative delta, so I wanted to make sure y'all knew what was going on so we could compare it. So I wrote the negative out in front, and then I did final minus initial, and now on the right-hand side, I'm going to write the formula negative mg times y2 minus y1 like that. Now you can see that the negatives could in principle cancel out, in which case you'd say u at 2 minus u at 1 is equal to, now I'm going to distribute the mg, it's going to say mg y2 minus mg y1, and now you see, oh, this mgy2 must be u at 2, and this mgy1 must be u at 1. So that tells us specifically u of y is equal to m times g times y. And you might say, well, what about the origin of coordinates? Isn't that going to matter? It's going to matter in the sense that you've got to choose your own coordinate origin and that sort of stuff. But it turns out, because we never really care about the actual potential energy, we always care about the change in potential energy. Because of that, if I choose a y equals 0 that is right here, and you choose a y equals 0 that's right here, it's going to turn out that when we subtract the change in potential energy, in other words, when we subtract final potential energy minus initial potential energy, mine's going to have my origin chosen, and it's going to be subtracted out, and yours is going to have yours, and it's going to be subtracted out. So it's not going to matter either way. But that's the actual process, and we got that from that theorem I just showed you. So the prescription is if you want to find the scalar potential for a vector field that you've determined to be conservative or that you assume is conservative, then you just calculate the work done again by that friction force in moving it from one point to another, and you set that equal to the negative of the change in potential energy, and that should allow you to figure out what the potential energy function is. In this case, it had happened to be only a function of y, and since we use the F is equal to mg, we know that's only applicable for places where basically you're comparable to the sea level of the earth. If you go, much higher than sea level of the earth or much lower than sea level of the earth, it's not going to be a big deal as long as you're like earthbound. So, for instance, the deepest point in the Marianas Trench only results in a change in G of about 0.3%. And if we go to the top of Mount Everest, it's going to only account for about a 0.3% change in G. So, from the top of Mount Everest all the way down to the bottom of the Marianas Trench, if you're only going for one, maybe two decimal places, then that should be plenty fine. If, however, you start to go a distance above the Earth's surface that's comparable to the radius of the Earth, then you have to go back and not use F equals mg. You have to use F equals g m1 m2 over r squared, and we'll do that later. But so far, we now have the potential energy, and that's what this is called, potential energy function for approximately sea level or terrestrial elevations. Meaning, if it's somewhere that people have been on the earth, then chances are, and I say on the earth, I'm not talking about, people that jump from extremely high aircraft that are even higher than Mount Everest. That would be a little bit different story, even though I still think it's pretty low. I don't think they do much higher than Mount Everest. I know you can't live for very long, even at the elevation of Mount Everest if you just drop there. So that's a little bit different. But the main thing is this is called the potential energy function, and it stands as a scalar representative of the gravitational force weight equals mg. So we have that. Now let's look at an example with this so you can see what I mean about having different origins or different y equals 0 positions, and you'll see that it really doesn't matter. Any questions on that, anyone? All right. So what I'm going to go to first is example 8.1. Oops, I wanted blue. And evidently my program wanted to change my writing to something that looked better. So example 8.1, it says potential energy changes for a roller coaster. A 1,000 kilogram roller coaster car moves from point 1 to point 2 and then to point 3. What is the gravitational potential energy at points 2 and 3 relative to point 1? That is, take y equals 0 at point 1. B, what is the change in potential energy when the car goes from point 2 to point 3? In other words, we're wanting to calculate delta U at that point. And then part C, repeat parts A and B, but take the reference point y equals 0 to be at point 3. So let me write down what we know, and then I'll draw a diagram, and that should help you. So I'm going to say M is equal to 1,000 0.0 kilograms, and that's just my way of trying to force this to make sure it has all four of those digits as significant. We are going to say, well, actually, at this point, it's just best to draw the roller coaster. So I'm going to draw the roller coaster. It has a flat spot and then a hill that goes up, and then it has a drop that goes down. and then it's level again. And what we're going to say here is that there's a different height for each of these places. This place right here is point 0.1. This place up here is point 0.2. And this place down here is point 0.3. Now, what we need to know is that this height is 15.0 meters from here to here, and then this height from here to here is 10.0 meters. And what we know want to know for part A, and I should write that back in blue, let me do that. What we want to know for part A is the potential energy U at 2, and I'll say sub 1, which means at 2 relative to 1, and U at 3 relative to 1 is a question mark. Point Part B, they want to know the change in potential energy, so I'm going to say delta U, and we're supposed to be going, what is the change in potential energy when the car goes from point 2 to point 3? So sometimes I choose to write this with an arrow because it's not always crystal clear if I write delta U 2 3, which I would normally personally prefer to write this as 3 2. It's not always clear whether the 3-2 means I ended up at 3 and I started at 2, or I ended up at 2 and I started at 3. So it's sometimes nice to just write that with an arrow, and that fixes it. So there's part B. And then part C, they want to know U at 2 relative to 3, U at 3 relative to 3, and they want to know delta U 2 to 3 equals question mark, and I'll subscript at 3, even though I really don't have to, because what I've been saying here is when you do this, you're going to see that the change in potential energy is independent of the coordinate origin that you chose. All right, so solution. What we know is potential energy U of y is equal to m times g times y. So for part A, we're going to say U at 2 relative to 1 is, notice at point 2, we're 10 meters higher than point 1. So I'm going to say for A, this is y equals 0. For C, this is y equals 0. So that's what we're doing here. So I just did U at 2 relative to 1, and of course that's going to be 1,000 kilograms times 9.80 meters per second times the height, which is 10.0 meters. So the potential energy is, obviously it's going to be 10,000 times 9.80. So, oops. And that gives me 9.8 times 10 to the fourth joules is equal to U at 2 relative to 1. So I'm going to go ahead and circle that as one of my answers. And now I'm going to do U at 3 relative to 1. That's going to be 1,000 kilograms times 9.80 meters per second. Now the height from 1 up to 3 is in fact a negative, so it's going to be negative 15.0 meters, like that. So now I'm going to take 1,000 times 9.8 times negative 15, and that's going to give me 1.470, actually negative 1.470 times 10 to the negative fifth, excuse me, 10 to the positive fifth, times 10 to the fifth joules is equal to U at 3 relative to 1. So that's another answer for part A. So now we have the answers for part A as follows. Part B is where we're asked to find the change in. So now I'm going to say B delta U 2 to 3 sub 1. Again, that sub 1 is redundant because it turns out it's not going to matter. But either way, we'll show you that now. So now I'm supposed to take U of 3, which is negative 1.470 times 10 to the fifth joules. And I'm sorry that 5 looks exactly like a joule, so I should probably write a little better than that. So it's that. And then I'm going to subtract from that 9.80 times 10 to the fourth joules. And from this, I get negative 1.470 times 10 to the fifth minus 9.8 times 10 to the fourth. And that gives me negative 2.450 times 10 to the fifth joules is equal to delta U 2 to 3. So that is part B, and we now know the change in potential energy and going from 2 to 3. Now in part C, we're going to do the same thing as we did for A and B, but now we're going to do it all relative to point 3. So C U at 2 relative to 3 is going to be 1,000 kilograms times 9.80 meters per second times now the height of 2 relative to 3 is in fact 25 meters. So I get 1,000 times 9.8 times 25, and that gives me 2.450 times 10 to the fifth joules is equal to U at 3 relative, or excuse me, U at 2 relative to 3. So I'm going to go ahead and box that off. And now I'm going to say U at 3 relative to 3 is equal to 1,000. I'll leave the units off this time, too much junk to write. 9.80, and this time the height is 0.0 meters. So this one's going to be just 0 joules equals U at 3 relative to 3. Of course, that should be 0 because we know if you're calling 3 y equals 0, then the potential energy at y equals 0 is supposed to be 0. So now we can go ahead and say that delta U 2 to 3 is clearly equal to the potential energy at 2, the potential energy at 3 minus potential energy at 2. So that's going to be 0 minus 2.450 times 10 to the fifth joules. And you see that that is equal to negative 2.45 times 10 to the fifth joules. And that's exactly what we got before using an entirely different y equals 0. Any questions on that? All right, so that's the big deal. That's what happens because notice it's normally a change in y that you're calculating, and if you're using, a origin that's 15 meters higher than the other case, then that plus 15 is going to show up in both the U2 and the U3, but in one case it's going to be positive, and the other case is going to be negative, so you end up getting 15 minus 15, so it's going to cancel out. All right. And that's exactly the answer that your book got, except your book was using everything as if it was two sig figs instead of three. And because of that, they got just plain 2.5 instead of 2.45. Now, the elastic potential energy, we've already worked that out. I did that integral before, but basically what we can say is elastic potential energy. Remember, this all came from F spring is equal to negative K times X. And what we got was that U turns out because U is going to be the work done. We calculated the work done, blah, blah, blah. But what we found was the work done, which we're now calling kinetic energy, or excuse me, potential energy, is 1/2 kx squared. And that's what it is, whether there is a compression by an amount x or a stretching by an amount x, it's always going to be 1/2 kx squared. So we can look at it as if U elastic, this is the way your book's doing it, except they used the lowercase e and the L, of x is equal to 1/2 k x squared, like that. All right. And of course, we always have the ability to come back and compute F. So let me take a second now that we have this formula here, which is the same as this formula, and all of them stem from this. So just so you have all that, I wanted you to have those. But I was telling you earlier that F is equal to the negative gradient of U. So now I want to show you exactly what we mean by that gradient. So the theorem that we talked about said that F is equal to the negative gradient of U. So it helps to help you understand what this is. I'm going to say negative. And then what I want you to understand is that U is a vector, if you will. So it's going to be pulling that U out in front. I'm just going to put out some curly brackets, and the or the x component of the gradient is I hat times the partial with respect to x. And remember, the u or the gradient is supposed to have a blank spot next to it, where in this case it happens to be the function u that's next to it. I'm just leaving the space so you can see what the gradient would look like, plus j hat, the y component, is the j hat times the partial with respect to y, again leaving a space, and k hat, partial with respect to z, again leaving a space. But all of that is operating on u, which could be a function of x, y, and z. Because of that, what we get is negative partial of u with respect to x times I hat minus the partial of u with respect to y times j hat minus the partial of u with respect to z times k hat. That is the gradient of u. And of course, the negative of the gradient of u is the actual force. So now you see what the force is. Alternatively, of course, if you wanted to compute that cross product, all this stuff right here is just called the gradient. But there's also a divergence. So we could say divergence. And for the divergence, what we have is del dot some function. Let's say let's say f just for the heck of it, because that's one you could possibly calculate, and del dot f because it's a dot product. The f must be a vector itself. So what we have in this case is uh, the partial of f with respect to, in this case, we're actually taking the x component of f, so the partial of f with respect to x dx plus the partial of f sub y with respect to y plus the partial of f sub z with respect to z. And that's what the divergence of it is. If you wanted to break it down to see how that happened, you would say I hat partial with respect to x plus j hat partial with respect to y plus k hat partial with respect to z dotted with I hat f sub x plus j hat f sub y plus k hat f sub z. And when you dot product that, that means the partial of f sub x with respect to x is the part that's going to get the x derivative, and the partial with respect to y is going to hit the j hat component, so that's partial f sub y with respect to y and partial f sub z with respect to z. So that's, again, same thing we got before, but that's what the divergence is. Similarly, we can also define the curl, which is also called the rotation. So curl, well, darn it, R rotation, and that's given by del cross f, which the cross product, we've been teaching you how to do that with the determinant. So the determinant is going to be the determinant of I hat, j hat, k hat, partial with respect to x, partial with respect to y, partial with respect to z, and then f sub x, f sub y, f sub z. And in this case, it ends up becoming del cross F is equal to, and I told you the trick before about you cover up the I hat, and then that makes you cover up that column and that row, and then that leaves you a little 2 by 2 matrix in the bottom right hand corner. And since the I hat is in the 1 1 slot, it's the first row, first column, you raise -1 to the 1 plus 1 power, because that's the two subscripts on the I hat, and that means -1 to the 2 power, which is +1. So I just take the regular determinant, and in that case, it's going to be the partial of f sub z with respect to y minus the partial of f sub y with respect to z, and all of that is multiplied by the I hat. Now I do the j hat for this one, and when I do the j hat, that was one in which it's in the place 1 2, meaning the first row second column. And when I raise -1 to the 1 plus 2 power, that's -1 to the 3 power, which is -1. So in that case, I still have that little 2 by 2 matrix left over, but it's 2 over here, and then there's a column that we're ignoring, and then there's 2 over here. And we're going to do the determinant in the backwards order to deal with that negative. So instead of going top left times bottom right minus top right times bottom left, I'm going to do it the other way, top right times bottom left minus top left times bottom right. So in this case, I'm going to write plus. Now I've covered up the j, and that's going to leave the partial of f sub x, or partial of f sub x with respect to z minus the partial of f sub z with respect to x, and that is the j hat component. And then finally, The k hat, I cover that up. That one is the first row, third column. So 1 plus 3 is 4. Negative 1 to the 4 power is 1. So I'm just going to do the normal determinant, but I do have to cover up the right column and the top row. So that leaves me the bottom left corner as the 2 by 2 matrix. And I'm just going to do top left times bottom right minus top right times bottom left. So the partial of f sub y with respect to x minus the partial of f sub x with respect to y times k hat. That is the curl of the function. Now, if you did all these computations and it automatically came out 0, then you know the force is actually a conservative force. But that's how you do it. Hopefully that helps you. Now you know how to calculate the gradient of something. Now you know how to calculate the divergence of something. And now you know how to calculate the curl of something. Now let's go to example 8.2 in case. But first, does anybody have any questions? It's just Michael now. Ugh. All right, looks like Michael's good. Now, last time I was working this example 8.2, and it looked like the book might have an error or a typo or something, but it might be that I made a mistake. I'm going to work it out and just show you what I'm doing. So let's say example 8.2. And what we say is U, the scalar potential, suppose U of x is equal to negative ax over b squared plus x squared, where a and b are constants. Okay? And what they want to know is what is f as a function of x. So they want to know what is f of x. Now, in this case, the potential energy function only depends on x, so it's only going to come out in terms of x, and that means it's only going to have the x component, because if you don't have a derivative with respect to y, then you got no y component. If you don't have a derivative with respect to z, then you have no z component. So this force only acts in the x direction, but it is a function of f, and specifically, solution f is equal to the negative gradient of u. And in this case, it means f sub x, which is a function of x, is only going to be the negative partial of u with respect to x. So that's what I got to compute. I'm going to start off just by computing partial of u with respect to x, and then I'll just multiply it by a negative later. So partial of u with respect to x is equal to the partial with respect to x. And I'm going to do this a way other than using the quotient rule, because I can derive the quotient rule. I can remember it with a little bit of work in my head, but it turns out it's a lot easier just to remember the product rule, and that automatically leads to the quotient rule. So what I'm going to do is say that this is negative ax times b squared plus x squared raised to the, and actually I didn't mean to do a square bracket there, but raised to the negative 1 power. So I can just treat this as a product rule thing. And the way we take the derivative of a product is, in the first case, we take the derivative of the first factor and multiply it by the second factor. And then in the second case, we add to that the first factor times the derivative of the second factor. So the derivative of negative ax with respect to x is just negative a. And then, of course, we still have b squared plus x squared to the negative 1. Now, the other part of the product rule is the negative ax is unaltered, but now I've got to take the derivative of b squared plus b squared plus x squared to the negative 1 power. And what I do is I first take the derivative of a function raised to the negative 1 power is negative 1 times that function raised to the negative 2 power. So b squared plus x squared to the negative 2 power. And now I've got to take the derivative of that function with respect to x, and the derivative of b squared plus x squared with respect to x is 2x. like that. So I can continue on, and what I'm going to get is negative a over b squared plus x squared. And then I'm also going to get a negative times a negative. It's going to give me a positive. So that's a positive. And now I have 2ax like that. All of that is over b squared plus x squared. And of course, that's raised to the 2 power as well. So if I wish to get a common denominator, I'm going to have to multiply this first fraction by b squared plus x squared over b squared plus x squared. So it's going to be negative a times b squared plus x squared over b squared plus x squared to the 2 power plus 2ax over b squared plus x squared to the 2 power. So now I can say f sub x of x is equal to the negative partial of u with respect to x. So now I need to take what I have and multiply it by negative 1. And when I do that, I get a times b squared plus x squared minus 2ax over b squared plus x squared squared. So now I've multiplied it by the negative, and I might want to make it a little neater maybe. So what we're going to try to do is it looks like we have a common factor of a that we can pull out. So I'll pull out that common factor of a, and that's going to give me a times b squared plus x squared. Oops. Looks like I might have dropped an X somewhere. Did I? Oh, yeah. Notice this. When I did this right here, I had an X times an X. So this should have been an X squared. And luckily I caught that now. So I'm going to go ahead and add it in. Let me write it in red so y'all know where I put it. And you can look back really quick. So that's that there. So I've got A times B squared plus X squared, which is the first term. And then minus 2 times x squared, like that. And then, of course, all that's over b squared plus x squared quantity squared. So now you can see x squared minus 2x squared is going to be negative x squared. And now it gets to the final result. The x component of f sub x is in fact equal to a times b squared minus x squared over b squared plus x squared to the 2 power, and that's the total answer. And that is exactly the same answer the book got. There was a midpoint where they got the 2 times x times the ax, and that was what was throwing me. But this time it turned out right, so no problems. Anybody have any questions on this? All right. So now I've worked out all the details regarding the gradient, the divergence, and the curl, even though the gradient or the divergence and the curl we're not using, but the gradient is definitely fair game right now. Now, once we had this, then we need a concept of conservation of energy. And I want to tell you the way I do it. I'm going to tell you the way your book does it. And you can use any of them you want, but I'm going to predominantly just stick to my method. So right here, I'm going to say conservation of energy. Oh, great. I hate it when it does that. I write so neatly, and then it automatically changes it. Conservation of energy. And of course, you probably recognize by now when I say a force is conservative, now you know why it's called conservative because it allows for conservation of energy. Other ones don't. But that being said, I'm going to tell you exactly the way your book has you do it and exactly the way many books have you do it. But I'm also going to show you what I use, and that's what I'm going to use. So, what we have here is a conservation of what we call mechanical energy. And mechanical energy just involves potential energy and kinetic energy, that sort of thing. So when we say conservation of energy, we mean the total energy equals a constant. Now, the types of energy we've learned about so far are potential energy, which is given the symbol U, and kinetic energy, which is given the symbol K. So, what you might say is U plus K equals a constant. So that is actually one way we could try to solve conservation of energy problems is we just always set U plus K equal to a constant. Of course, that's not very helpful because we'd have to take U plus K and then we figure out what that constant is, and then we have to set that equal to another U plus K for later on for after some event or whatever, and then solve for one of the either the U or the K or some part of the U or the K. So what we often do is instead we'll say U initial plus K initial is equal to U final plus K final. And that's another way we could do it. Okay. But you could also do something like this. You could pull the U initial over to the right hand side with the K initial. And if you did that, then you would get U final minus U initial plus K final minus K initial is equal to 0. And that's another way of writing it. But normally we would write that as delta U plus delta K equals 0, and I'll call that 3 as well because that's just two versions of the same thing. So those are three different ways that are more like what your textbook author uses. Now, what do? I like to take into account all in one fell swoop. I like to take into account the possibility that some energy could be added to the system via a non-conservative force. I like to take into account that some energy could be stolen from the system due to some non-conservative force. I like the idea that some of the work could be taken from it by the system doing work on the surroundings or something like that, or by the surroundings doing work on the system. So my way is this. I say UI plus KI plus work in is equal to U final plus K final plus work out plus E loss. Now, this is true for the other versions as well. I just hadn't stated it at that point, but each of those U's in these three equations that I gave you in green, they could stand for multiple different terms. They could be, for instance, the potential energy due to one particle having a height y, which would be m1gy, and then another particle which has a height y2, say, that would be m2gy2, and so on and so forth. So all these terms could be multiple terms, and the same is true with my version as well. What I normally use for work in, for instance, is, and I'll show you an example in a second, is something that someone could actually use as some energy added to the system. So if you wanted it to be more symmetric, you would add on to the left hand side and say plus, instead of E loss, you could say E gained. So you could stick that term right in here, and then it would be more symmetric. It'd be UI plus KI plus work in plus E gained equals UF plus KF plus work out plus E loss. But I've always found it enough to just have the W in on the left hand side and the E loss on the right hand side. Specifically, like I said, because these terms can have multiple different meanings. You can have, three different terms just associated with work in if you want to. And not only that, what you're calling work in, I might call E gained, and what you call E loss, I might call work out or something. So that's the way I'm going to work it. And now I'm going to show you one big example that hopefully helps you understand better how to use my version of it, which again, you can use the version that the book has, but you'd have to wait to the section where they talk about non-conservative forces and trying to incorporate them. So let me show you an example. What we're going to have here is a little girl sitting on a sled on top of a mountain. So here she is on her sled. And of course, she has a little ponytail. You know, like all girls have ponytails, evidently. And her father's going to give her a little push. So I'm picturing her father as giving her a push like this. And what's going on there is a force equal to 100.0 newtons. And it's going to be pushed through a distance of 3.00 meters. So that is a classic example of work put into the system. But another person might say that's a classic example of E gained by the system. So you could calculate the work done by the father and realize that that's going into energy for the system and set it equal to the same number, but you're calling it E gained instead of work in. That's fine too. Now, the kid is at the top of a hill, so they're going to go uh, from this flat spot on the top of the hill. It's going to be a steep slope downward, and then she's going to run into level ground. And at that point, she's going to run into more or less like a rumble strip, if you will. So that's supposed to be a frictionful area that can hopefully slowly bring her down to a lower speed. However, in the event that she makes it all the way past that, then we're going to switch back to a non frictionful end and we're going to have a bumper that can catch her. It's a big padded thing, and that big padded thing is going to be attached to a ginormously long and large spring, and that spring can be compressed to bring her down to a speed of zero as well. The spring constant for that spring is going to be 10,000 underscore newtons per meter. The coefficient of friction, which is kinetic, by the way, is 0.400. And I'm going to say that this distance right here is 10.0 meters. Actually, let's make it 20 meters. Let's make it 40 meters. Okay. And finally, I'm going to say that the height difference here is h equals, no, let's make it 200 meters. H equals 200 meters. And that's the height from here to here. And we're going to say the little girl and her sled has a mass of 75.0 kilograms. So, part A, how fast is she going just before hitting the rumble strip? In other words, before hitting the frictionful area. Okay, so that's the first thing I want to know. And then part B is how far along the rumble strip does she make it? Because the rumble strip could, in principle, bring her down to zero, in which case I'd like to know how far she goes. Otherwise, in other words, if she doesn't actually come to a stop on the rumble strip, how fast is she going when she hits the bumper? Bumper. I know that E looks like it's a little elongated, but everybody follow that question? And then finally, assuming that she actually does make it all the way through the frictionful area, we want to know by how much does she compress the spring before coming to a stop. So C, by how much will the spring be compressed to stop her? Again, of course, that assumes that the first part of B wasn't the case because the first part of B was imagining that she came to a complete stop in the frictionful area before she got the full 40 meters. So that's what we're going to do. So now let me show you how we're going to do all this. I'm going to write my conservation of energy equation, which is U initial plus K initial plus work in is equal to U final plus K final plus work out plus E loss, like that. Okay? Now, in this case, what I want you to realize is we're going to imagine that we're focusing on her just before the father pushes her, starts to push her, in which case her velocity is going to be zero. And we're going to imagine that the father's just going to push her real quick with 100 Newton force over a distance of 3 meters. And that's energy put in. But we're thinking that's going to happen more or less in an instant. So we don't have to think about kinetic energy being anything other than zero at the beginning. So with that in mind, I'm going to say kinetic energy is equal to zero initially. The potential energy, of course, is given by her height up on the mountain. So that's the 200 meters. The work in is what the father does, and the U initial, like I said, is mg times her height h. When we get to the bottom, the height will be zero because I'm going to take this as y equals zero as the height at the bottom of the hill. And uh, for part A, we're just trying to figure out how fast she's going when she hits the level spot. So for part A, the work out and the E loss is going to be zero. That's the way you work these conservation of energy problems. A large fraction of the terms are going to be zero. So let me put the numbers in for this first one with their units, but from there on out, I'm going to drop the units because it's too much to write. So in this case, I'm going to say 75. Actually, let me stick to blue. I'm going to say 75.0 kilograms times 9.80 meters per second times the height, which is 200.0 meters, plus the work in. Notice I drew the force as if it's horizontal. That's trying to tell you, hey, the force and the D are parallel, so the work done is just force times distance. So that's going to be 100.0 newtons times 3.00 meters uh, plus 0 is equal to, and that 0, of course, was K initial. And then the right-hand side is going to be 0 plus, and let me write this just for here. This is K initial, and this one is U final. Now, the kinetic energy final is going to be 1/2 times 75.0 kilograms times V final squared. And that's the V final right at this point right here. Let me draw it with a dot here. For part A. Okay. And there we have no workout and no E loss. So this is going to be plus 0. And like I said, that's workout and E loss. So with this in mind, I'm going to go ahead and compute these numbers. 75 times 9.8 times 200 is equal to 1.47 times 10 to the fifth times 10 to the fifth joules plus 300 joules is equal to 75 times zero point 0.5 should be 37.5. So it's going to be equals 37.5 kilograms times V final squared, like that. So I can solve for V final by saying V final is the square root of the 147 times 10 to the 1.47 times 10 to the fifth is really 147,000. So 147,000. And then when I add 300 to that, that's going to be 147,300 joules. And technically, that 3, that 0, and that 0 are not sig figs. So that's why I put them there. And then I'm going to divide all that by 37.5 kilograms. Now, if you look at a joule is a Newton meter, and a Newton is a kilogram meter per second squared. So a joule being a Newton meter is a kilogram meter squared per second squared. So if I divide that joule by a kilogram, I just get meter squared per second squared, and the square root of meter squared per second squared is just meters per second, and it's going to be pretty big. So we're going to say plus 1.47 10 to the fifth. Now I'm going to say, actually, I'm going to put it in here. I'm going to say 147,300 divided by 37.5. That gives me the square root of 30, or excuse me, 3,928. And now I'm going to take the square root of that. The square root of 3,928 is about 62.67 meters per second. So that's the answer for part A. And that's quite fast. Remember, that's about, if you multiply that by about 2.2, you're looking at 150 miles per hour. That's pretty dangerous for a small child on a, on a sled. All right. Now we're going to, since that was part A, and this was all part A. Actually, I should have wrote that A in blue. So now we can start doing like part. Darn it, I was thinking B, so I wrote down B. Now we can start thinking about doing B. It says for how long will how far along the rumble strip does she make it? So what we're looking at here is does she have enough energy to make it for the whole 40 meters? If she did, then the E loss or the workout, whichever one you wanted to consider it for the rumble strip, if we calculated that, what we'd have to find out is that her energy on the left-hand side of the conservation of energy equation, is that energy bigger than the energy that she would expend in going the full 40 meters? So let's take a second and realize that the left-hand side is the total energy, and that's equal to 147,300 joules. That's the total energy. Now let's look at the energy loss due to friction, or the work out is equal to, in this case, we've got mu kinetic times the normal force. That's the actual force of friction. And in this case, it's going to actually point in the opposite direction. But when you use my version of conservation of energy, none of your terms are negative except for ones that have the negative built into the formula, which we're going to learn about later when we do the potential energy for areas where you're not close to the surface of the Earth. We're going to end up getting U is equal to negative GMM over R, and that has a built-in negative formula. We're not supposed to use any negatives on this one, so even though we're actually doing work against friction, so that's a negative amount of work, we've put it on the right-hand side to deal with that, okay? So we don't need that negative. But the friction force is mu k times the normal force. The ground is level, so the normal force should just be mg. And in fact, we're going a distance d, and the force is a constant. So the work out will be mu k times the normal force times the distance d that we travel across the rumble strip. So in this case, we'll say max. In other words, the max amount we can get out is going to be 0.400. The kinetic coefficient of friction, like the static coefficient of friction, has no units. The normal force is m times g, so that's 75.0. I told you I wouldn't use any more units, so I'm going to ditch them. And times 9.80. So that's my mu times mg. And then I'm going to check that versus 40.0 meters. So zero point 0.4 times 75 times 9.8 times 40. And in this case, it gives me 11,760 joules. And you can see that that is way less than 147,300 joules. So clearly we can tell that it will make it across the whole rumble strip. She will cross the rumble strip. Okay? And that leads us to part B of B, which is how fast will she be going afterwards. So really what we're going to do now is we're going to use conservation of energy, UI plus KI plus work in is equal to U final plus K final plus work out plus E loss. So again, you could have called that W out max that we said was the work done against friction. We could have called that E loss. That would have been fine. The main thing is what I'm going to do is take the left-hand side of this, which is 147,300, 300 joules. I'm going to set that to the left-hand side. And what I'm going to do now is I'm going to say equals 0 for the potential energy plus 37.5 times V final squared plus now I'm going to put in the E loss, and of course the E loss was the workout maximum that I did a second ago. In this case, it's going to be 11,760 joules. So that's basically the whole conservation of energy equation with only the relevant parts. So now I've got to solve for V final, only now I'm solving for V final at this spot right here. Part B of B. So in other words, the second part of part B, that's where we're figuring it out. So what this tells us is that V final is going to be equal to the square root of 147,300 joules minus 11,760 joules divided by 37.5 kilograms. And when I do that, I get 147,300 minus 11760. Now I'm going to divide that by 37.5, and that gives me 3,614. And that's meters squared per second squared. Now I'm going to take the square root of that, and that gives me just a mere 60.12 meters per second. So we haven't slowed down very much. So we now found that once she comes out of the rumble strip, she's still going about 60 meters per second, which is on the order of still about 140 miles per hour, maybe. So still pretty darn fast. Now, with that, they want to say, by how much will the spring be compressed? Well, what we know is the energy she has going into the spring is exactly the energy she had at the end of the rumble strip. So basically, the 147,300 minus the 11,760, that's how much energy she has. And all of that is going into, let's call it work out, where we're going to compress a spring. So for part C, I'm going to do it like this. The conservation of energy says it's 147,300 joules is equal to 0 plus 0 for the kinetic energy plus the energy that we lost due to the friction rumble strip is 11,760 joules. And then plus we have work done out, which is 1/2 of 10,000 newtons per meter times x squared. So we're just going to solve for x squared. And in this case, we're going to say 147,300 minus, and actually I'll put all this in parentheses, minus 11,760 divided by 5,000, and that gives me 27.11, and that's meters squared, taking the square root of it. So now I'm going to take the square root of that, and we're going to get 5.207. And that's suggesting that we would actually compress that spring by about 17 feet. So obviously, this problem is not very physical. It would definitely put a child in harm's way and stuff of that sort. And we're getting really wild numbers. Compressing a spring by like 16 feet is kind of a big deal. You'd have to do a lot of engineering to make sure the spring didn't bulge out left or right. But the main thing is, by doing this, you've now seen how we can use all the individual terms of my conservation of energy equation. Any questions on that? All right, with that in mind, now we're going to go on. Your book goes on to problem solving using conservation of mechanical energy and stuff like that. So we can solve a few of those problems. Let's see what we want to do next. I'm going to do example 8.3. Example 8.3 says, if the original height of the rock in figure 8.7 is y1 equals h equals 3.0 meters, calculate the rock speed when it has fallen to 1.0 meters above the ground. So what we're saying is y1 is equal to h is equal to 3.0 meters, and y2 is equal to 1.0 meters. What we want to know is, what's the rock speed? V final equals question mark. Now, they're referring to figure 8.7, and when I look at figure 8.7, it's just a person holding a rock up like this, okay? And he's going to drop it. They didn't give us anything about the weight of the rock or anything like that, or the mass, but if luck allows, we'll actually solve it without it. So again, I'm going to use my equation, So I'll write solution, and my version is U initial plus K initial plus work in is equal to U final plus K final plus work out plus E loss, like that. And of course, we know U is equal to mg times Y, and we know K is equal to 1 half mv squared. Again, that's the formula for when we're not going speeds comparable to the speed of light. If we get comparable to the speed of light, then we need to use a different relativistic formula, which I told you was gamma minus 1 times mc squared. But here's how we do it. So in this case, what we're going to do is we're saying the initial potential energy is m times g times h because they gave us the symbol h. It's 3 meters, but I'm going to keep it as a symbol. So that's the ui. The initial kinetic energy, since he's just going to drop it, he's just dropping the stone, the initial kinetic energy is 0. And of course, he's not giving it any kind of push down or any kind of push up. So there's no work put into it. So that's going to be plus 0. And then when it gets down to a height of y equal 1 meter, its potential energy is not 0. If we allowed it to go all the way to the ground, then we could say the final potential energy is 0, and it'd be a little bit easier for us. But that's not what they told us to do. They're wanting us to say m times g times y2, like that. That's the final potential energy. And what they want to know is how fast it's going. So they want 1 half m v final squared, but the workout is going to be 0 because we're not imagining compressing any springs. The E loss is going to be 0 because we're not working against friction or anything like that. So that's how we do all this. We can see right now that we can divide the left hand side by M and the right hand side by M, and that actually cancels out all of the M's that we have, which is good because we didn't know what M is. And this also tells us that the answer is going to be independent of the M, which is exactly what Galileo said, that all bodies fall at the same rate if you ignore air resistance. So what we end up getting is GH, actually, let me write it, GH equals GY2 plus 1 half M, or excuse me, plus 1 half V final squared, like that. I'll multiply both sides by 2, and now we'll get 2GH is equal to 2GY2 plus 1 or plus V final squared, and that gives us that V final is equal to the square root of 2G H minus Y2, like that. Now, if you notice, that looks just like Y equal, or let's say, that looks just like V squared equals V0 squared plus 2A Y minus Y0. This is the exact same equation, except V0 is 0 and A is G and Y0 are H and Y2. So it gives you actually exactly back the same kinematic equation. But in this case, you couldn't just use the kinematic equation because you don't know that the acceleration is a constant, and that's when that equation is valid. From this, we figured out that evidently that equation is valid, but you couldn't just write down that kinematic equation. In fact, if you did that on a test, I'm not going to give you credit. Okay, so now we can go ahead and solve it. I'm going to put in the numbers. It's going to be the square root of 2 times 9.80 meters per second times h, which is 3.0 meters minus 1.0 meters, because that's y2. And from that, we get square root of, square root of 2 times 9.8 times parentheses 3 minus 1 close parentheses And that gives me 6.261, which is two extra sig figs than we had. So that 6.261 meters per second is the final velocity. And that's how that one's done. Anybody have any questions on that? All right, that looks pretty good. Now let's look at example 8.4. I think this one's pretty straightforward. We can do this. So let's do example 8.4. Never fails. I always do the same thing. Example 8.4. Assuming the height of the hill in figure 8.8 is 40 meters and the roller coaster starts from rest at the top, calculate A, the speed of the roller coaster at the bottom of the hill, and B, at what height it will have half the speed. Take y equals 0 at the bottom of the hill and ignore friction losses. So looking at figure 8.8, okay, in this case, it's a slightly different roller coaster than we had before. It looks something like that, okay? And they're saying the height from here to here is y, okay? And now we're looking at example 8.4. They did tell us y is equal to 40. I'm going to add extra sig fig. That's going to be 40 meters. And what we want to know is we choose point, oh, excuse me, from rest. We're going to say up here, V initial is equal to 0. So V initial equals 0. And what we want to know in part A is the speed of the roller coaster at the bottom. So we want to know V final for part A equals question mark. And right here is the V final for part A. And then part B, they wanted to know at what height it will have half the speed. So Y equals question mark if V equals 1/2 V final. So solution, U initial plus K initial plus work in is equal to U final plus K final plus work out plus E loss. Now, all these work ins, workouts, and E loss are all 0 here because they told us to ignore friction and stuff like that. So in this case, I'm going to start with nothing but potential energy. So it's going to be M times G times 40.0 is the meters. Again, I'm leaving the units off right now, and we don't know what the mass is yet, so we're hoping we won't need that. The initial kinetic energy is going to be 0. This is this term, this is this term, and the work in is going to be 0. And the final potential energy is actually going to be 0. So that's how what's nice about potential about the conservation of energy. A lot of terms drop out. And then the final kinetic energy is going to be 1/2 mv final squared. So that's that term plus 0 plus 0. And you can see automatically that if we divide both sides by m, then the m disappears. And we basically have v final is the square root of 2gf or 2gy. So v final is equal to the square root of 2 times 9.80 times 40.0. Again, I've worked out these units inside of here in my head. I just did it again to make sure they all work right. But basically, a 9.8 has meters per second, and the 40 has meters. So that's meters squared per second squared. Taking the square root of that gives us meters per second, and that means the velocity. So I'm going to take the square root of 2 times 9.8 times 40, and that gives me 28.0. Actually, I did use 3 sig figs, so 28.0 meters per second is the velocity that it has at the bottom of that hill. Any questions on that one? Now, what we'd like to know is what height at which it will have. That was all part A, by the way. We'd like to know at what height it will have half that speed. So what we're going to do for this one is part B. We're still going to say UI plus KI, blah, blah, blah. So I'm going to get M times G times 40.0 plus 0 plus 0 equals. Now, in this case, we're going to have m times g times y, and this is the y that we're looking for. So I'll call that y 1/2, just because I know that's, when it has half the speed. So it'll just be a nice little reminder. And it has not only potential energy at that time, but it also has kinetic energy, and that is given by 1/2 m. And in this case, it's going to be 1/2 V final that we just found squared. And of course, we're still going to have a plus 0 and a plus 0 like we did before. And we can still, again, divide both sides by m. And that m is going to cancel out with that m. And this m is going to cancel out with these m's. So I just need to plug the numbers in. And plugging the numbers in is going to give me 9.80 times 40.0 equals 9.80 times y 1/2, which is what we're looking for. Plus, in this case, it's going to be 1/2, and then half of y final is 14.0 meters per second. So I'm just going to square that. I'm going to multiply both sides by 2. And that's going to give me 2 times 9.80 times 40.0 is equal to 9.80, is equal to 2 times 9.80 times y 1/2 plus 1/2. Oh no, I actually got rid of the 1/2. So now it's just going to be 14 squared. And 14 squared is 100, 180, 196. So this would be 196, like that. So now 2 times 9.8 times 40 is equal to 784. Equals 2 times 9.8 would be 19.60 y 1/2, and then plus 196. So y 1/2 is going to equal 784 minus 196 divided by 19.60. 784 minus, minus 196 gives me 588 divided by 1960, 19.60 gives me 30. So it actually reaches that speed when it's only 10 meters from the top. So it actually drops the height about 10 meters and it's already reached half that speed. And then the remaining 30 meters down below, it only jumps from 14 meters per second to 28 meters per second. Anybody have any questions on that? All right. There's a nice conceptual problem on example 8.5, so let me give you a drawing of that to make some sense of it. So conceptual example 8.5. So what we have here is two tracks, something like this, and then another track that I'll draw red, and this one goes like this, like that. So what we have here, ooh, I was getting ready to draw Genie there, and Genie got a big foot. Yay, this is Genie. And then up here is Paul. So the question is this: two water slides at a pool are shaped differently but start at the same height, h. Two riders, Paul and Jeannie, start from rest at the same time on different slides. Which rider, Paul or Jeannie, is traveling faster at the bottom? A. Which is faster at the bottom? And B. Which rider makes it to the bottom first? Okay. So for part A, since they both start at the same height and they both finish at the same height, basically what we've got for part A is V final for Paul is equal to V final for Jeannie. And the reason why is U initial plus K initial is equal to U final plus K final plus 0 plus 0 plus 0 using my version. And we also would say they both started with two riders start from rest, so the initial kinetic energy is 0, and at the bottom the potential energy is 0. So what we have is mgh for Paul is equal to 1/2 mv final squared for Paul, and mgh for Jeannie is equal to 1/2 mv final squared for Jeannie. And you can see that once you cancel out the masses, everything else is exactly the same, and that's why V final for Paul is equal to V final for Jeannie. Now, for part A, it's a little different because what you see is when they take off, Paul is barely speeding up at the point that we show right here. And in fact, at this point, Jeannie has already fallen all the way down here because her speed is so much larger because the change in height changed by so much. So her potential energy got really, really small here. So right here, let's say U is small, which implies V is big. Right here, directly above her, U is large, which implies V is small. because the potential energy wasn't able to change very quickly, so the kinetic energy couldn't change very quickly. So you see that right off the get-go, she's going much faster, and in fact, at every point, she's always going to be lower than Paul, and since she's always going to be lower, her potential energy is always going to be lower, which means her kinetic energy is always going to be lower. So that means Jeannie will reach the bottom first. Does that make sense? Any questions on that? All right. So that's that problem. We're looking at 7:24. We still got about 16 more minutes. Let's do this pole vault estimate problem. So here is example 8-6. And they say estimate the kinetic energy and speed required for a 70 kilogram pole vaulter to just pass over a bar 5.00 meters high. So we need M is equal to 70.0 kilograms, and we need H to be 5.0 meters high. Actually, I should say 5.00 meters because it looks like I'm starting with three sig figs. This is an estimate problem, so we really should be only reporting like one sig fig answer. Assume the pole vaulter's center of mass is initially 0.90 meters off the ground. So I'm going to say Y1 is equal to 0.900 meters off the ground and reaches its max height at the level of the bar itself. Okay, so that's where that is. And what they want to know is estimate the kinetic energy and the speed required for them. So what we want to know is K equals question mark and V equals question mark. What we have here is solution U initial plus K initial plus work in is equal to U final plus K final plus work out plus E loss. Like that. We're ignoring air resistance and stuff like that. So I'm going to say work in is zero, work out is zero, E loss is zero. And I'm sure the pole vaulter would say something entirely different because she's definitely putting a lot of work in that might be in addition to just running and stuff like that. Initially, her kinetic energy is going to be well, we actually need her kinetic energy to switch from kinetic energy to potential energy. And ideally, what's going to happen is she just comes to a stop as she reaches her max height. So the kinetic energy initially is going to be basically whatever kinetic energy we want. So that's the one we're working for. But the initial potential energy, I can't say that's zero because she has a specific or a center of mass that is zero point 0.9 meters above the ground. So I'm going to go ahead and write in all the terms. I'm going to say 70, oops. I'm going to say 70.0 kilograms times 9.80 meters per second times the height, which is 0.900 meters, plus 1/2 times 70.0 kilograms times V, which is the answer we're looking for, V squared, is equal to, now I want the height to be the 5 meters, so this is going to be 70.0. I'm going to leave the units off this side because we already worked them out on the other side. So I'm going to say 70.0 times 9.80 times, in this case, 5.00. And at that point, the kinetic energy should be zero. So I don't put zero there, and I could have just done it like that right there. So that's what we're ideally shooting for. And what we want to do is solve for that velocity there. So I'm going to go ahead and compute what 70 times 9.8 times zero point 0.9 is, and that's 61.74. Oops. That is 61.74 joules plus 35.00 kilograms times V squared is equal to 70 times 9.8 times 5, and that's equal to 343.0 joules. So I can subtract 61.74 from both sides, and I get V is equal to the square root 343 minus 61.74 gives me basically 281.3, and that's joules divided by 35.00 kilograms. So I'll divide that by 35, and now I'm going to take the square root of this, and that's going to be equal to 2.835 meters per second, and that would be roughly that. So I'd say about 2.8, 2.9 meters per second, which is not anywhere near what they got. And now I don't know why. What did I miss? Did I drop something? Or am I looking at the wrong problem? 0.95 meters, I got that. 4.1, I got that. Hmm. Yeah, that looks right. Hmm. Okay, so they more or less did the same, but yeah, they got a much bigger speed. They got 8.9. Uh, I'm gonna have to. It's 7:30. I'm gonna have to think about this one. I just on a whim decided to do it. I ain't worked it in years, but I don't see why this is a problem. I had initial potential energy, I had initial kinetic energy, and then I'm wanting all of that to turn into potential energy. And they're saying their kinetic energy that she had to be equal to mgy, which should be the same thing I got here. Did I do it wrong? Let's see. 70 times 9.8 times 5. That gives me. Oh, that's what it is. Okay. So I actually misread my calculator. The 343 was supposed to be 3,430. That's the problem. Okay, that makes more sense. Everybody see that? This number right here, that decimal is not supposed to be there. That decimal is supposed to be there. So I'm going to erase this. Everything I did was right, just other than, arithmetic. So so with this in mind, it's going to be 3,430 joules. Now I got to check and see if that 61.74 is right as well. So 70 times 9.8 times zero point 0.9. That, oh, nope, that was wrong too. That was supposed to be 617.4. Ooh. So 617.4. So now I can say V is equal to the square root of 3430 joules minus 617.4 joules divided by 35.00 kilograms. And that is 3430 minus 617.4. Divide that by 35, and now take the square root of that, and that gives me much better. That gives me 8.96 meters per second, And that's much more like what the answer in the book has. So sorry about that. I just actually my calculator's in scientific notation mode, and I just misread the exponent because I'm old and my eyes are crappy. So it's about 9 meters per second is how fast she needs to run, and of course 9 meters per second is about 2.2 times that for miles per hour. So that'd be 18 plus point 1.8, so about 19 miles per hour, nearly 20 miles per hour is what she needs to run. Anybody have any questions on that? All right. The one thing I want to tell you, even though I don't really have any more time, I've only got about 6 more minutes. I want to give you a little rundown on what power is because that's something we're going to encounter in this section. So, power is on average work done divided by time taken. That's the average one. But it also, we often run into cases where work is turning into potential energy and work is turning into energy or something like that. So we'll often say it's W over T, or we might say it's potential energy over T, or we might say it's energy divided by T. All of those are fair. Okay. That is very common for us to use for the average. And in fact, if you want the instantaneous, it's P is equal to dw dt or du dt or de dt, where again, all I'm saying here is the instantaneous rate of change of work, the instantaneous rate of change of potential energy, the instantaneous rate of change of energy. Any of those are fair game. And in fact, if you consider that work is equal to the integral of f dot dl, you might say, for instance, that work could be, if it was a constant force acting at a particular constant angle, it could be work is equal to F times L times cosine of the angle between them. And then, since the force is constant, power, which is dw dt instantaneously, would be d by dt of F times L times cosine theta. But remember, we're saying the magnitude and the direction of the force is a constant. So the F and the cosine theta are constants. And we just get F cosine theta times dl dt. But dl dt is just velocity. So this turns out being that power is equal to force dotted with velocity. That's why I kept the F cosine theta in there so that you could see that it was the equivalent of the dot product. So that's a result we use, and it's specifically only true if it's a constant force uh, causing a specific velocity v. Okay. Any questions on that one? All right. Well, we've covered all that I think I can fit in tonight. And really, to be honest with you, this is a huge fraction of the chapter on conservation of energy. I might not even do any more examples, but if I do, I'll do them next time, or I might do them on a video and just tell you guys to watch it. But we're pretty close to being finished, so you should be able at this point to do all the homeworks for chapter 8, and you're free to go. And feel free to ask me questions. I'll wait for as long as you need.